Hello everyone, this is week 10. Today we have a different topic. We are going to develop some function in C, and then we're going to integrate that function into Matlab so that it becomes kind of a Matlab executable. This is kind of a way of creating a DLL in Windows, which is used to basically um, incorporate different environments. Here we can extend Matlab capabilities using the plain C function, C language actually. So I think it is an interesting topic, so I wanted to include that too as a video. Now let's write an example function, a sum function in C that accepts two scalars of type double and returns their sum. Now let's call it the C sum.c function here. Let's include stdlib and well, yeah, let's call the function csum. We are going to return the sum, and let's have double a and then double b, and let's return a plus b. Of course, this is a trivial example. This is not what it is supposed to be, but we have a certain function. If we can accomplish this for a simple function, you can extend this to your needs. So yeah, we have a C function here. Now I can also compile this. Let's bring up some CMD here, the command window. Of course, we also need a function to test this. Well, do we really need to do that? I guess not. If you have GCC or G++, you can basically compile everything into an executable. Now, I'm not going to be able to compile this because we don't have an int main here, but yeah, we can maybe quickly add that int main and then return 0. Let's use the csum here for printf. Percentage double, actually something like this, plus this should be this. So it's basically, maybe we should call it double A, which is 2 for some reason, and then we have 3, double B, and then A, comma B, comma C sum, A, comma B, and then close this. Maybe a new line would be nice. There we go. Now this is the basic example now, and I can compile it into a printf, and maybe stdio is needed here. stdio. There we go. Now you can see on the left we have a main executable. When I run it, I get 2 plus 3 equals 5. So let's suppose this is a very complex algorithm and we want to include it into Matlab. What could be the reason behind this? Well, it could be a better performing algorithm when it's coded in a low-level language, and maybe in Matlab you're just interested in the results, not the execution itself. Then we can include it basically into Matlab. Let's see how we can do that. Now I'm going to get rid of this part because we are just going to compile this file and I don't have stdio. I could also maybe skip stdlib here. We'll see, because I'm not sure that we're using anything from it. So maybe we can get rid of it. So just a plain C file. Let's see. Now I'm going to destroy this CMD. Now we're back in Matlab. Now, in order to be able to do such a thing, first we need a compiler that is basically compatible with Matlab. So we will have a compiler which is called max, and as far as I know, if we invoke .h, it will pop up the help message here. And you can see that this is basically the compiler that we're going to use. This is a Matlab C compiler, Matlab executable compiler. We can compile the so-called max function. Now, a max function is a Matlab executable function. It can come from different languages. We can compile it with a max compiler, and we're basically good to go. Let's follow the link. Let's say yes. And there we go. Here we have the documentation. You can read the description, the documentation, and you can see here we use max like a GCC compiler, and we compile C files with a specific version if it's needed, and then we are going to be able to just use that. Now, I'm going to provide an example, so let's try to dive into it. Now, for this, we actually need since we've got rid of the main file here, the int main function here, we will have a sort of a Matlab main function, if that makes sense. Instead of having main like this, we will have something else, which is basically a void max function, Matlab executable function. So this is a wrapper that is used by Matlab in order to wrap this C file so that it is compatible with Matlab. We will use this max function in order to invoke our function, our actual function. But this max function here has some inputs, namely NLHS, number of left-hand sides, and then something called MX array, and then a pointer to it, PLHS, so left-hand side pointer, and of course their right-hand side version, because we have multiple outputs in a Matlab function and we can have multiple inputs in a Matlab function. This is basically what it is. It uses an int pointer and a special structure pointer, MX array, or class pointer, PRHS, which is going to be constant because the right-hand side is read-only at this point. We cannot change it. It doesn't make sense to change the right-hand side because it is an input argument given from Matlab. We should not be able to manipulate that. If we manipulate it, we might mess up stuff that we don't know about. So I can basically pop this in. So NLHS is basically num of left-hand side and pointer of left-hand side, and then the number of right-hand side and the pointer of right-hand side. Now, in order to separate this stuff, because I don't want to mess up the C function, I want to have it there. Let's actually create a new file and call it maybe m_sum.c. So I'm going to include this. Of course, before we do that, we need to include also the max.h header and also something called matrix.h. Now we get some errors because my code editor is trying to use Visual Studio Visual C++ as the compiler, and the compiler does not know where the max file or the matrix is. But actually, I have already set up my max compiler, so therefore I'm not going to use the Visual C++ compiler. So max setup C, as far as I remember. If we do this, it is configured to use Microsoft Visual C++ 2019 for C language compilation. So yeah, it's going to compile with a compatible compiler. So Matlab is going to use basically Visual C++ here. I don't remember the specifics now, but I guess we can also set up GCC here so that it uses GCC or some other compiler that is basically supported by Matlab. So let me just show you Matlab max compiler lists, maybe compatible compilers. So is it this one? Yep, it should be this one here. So you can go to the supported compilers by Matlab. Then you'll see a lists or tables here, which you can use then to download. For example, you can download MingV for Matlab, which is a 64-bit compiler. This is not actually the compiler that you might have already available to you. But if you have Visual Studio and then if you've installed Matlab or if you try to set up Max, it'll search for Visual C++ compilers. If you have that, it'll just use it as it is the case by mine. Here you can see you can also download from Matlab. You can see its compatibility. We're just going to use this basic stuff here, so we don't really care about this. But you can check this out. So now, yeah, the last thing that I might include here is going to be the see some file here. So let me see. Yeah, let's actually, since we have the implementation here, let's also have the header file csum.h. So basically csum here is going to be our library, sort of, or C function. We have this prototype in the header, we have the implementation here, and we should be good to go. So now I can include it here, in here. You don't really have to do this. You could just copy the definition and then compile the corresponding files, but let's do it the right way. So the last thing that we need here is maybe a build.m Matlab script, build.m. So clear CLC. There's something called clear max where all the loaded max files are going to be deleted from the memory. So this basically means that if we load a DLL, for example, we want to get rid of it, and then we want to compile it again. So it could be the case that it is loaded in a memory, the max file that we're developing here. We should basically erase it from memory, then replace it. If you have opened a txt file and if you don't close it, then you cannot delete it. This is kind of a thing that we need to care here. And other than that, we have actually something like gcc star.c. So it is going to be max star.c. I guess this should be it. If you have configured your compiler, this should basically work. So let's build it. There we go. We have compiled it successfully. Yeah, this is basically GCC, but we use max and we have a different main function that is compatible with Matlab. And there you go. You have compiled it. Well, of course, we can call this function now. This is called csum now. And you can call csum. And it does nothing. So it's actually a function, but it does nothing. So you can execute this, but we didn't do anything. So yeah, it does nothing here. So how can we change that? Well, first of all, we can check if, for example, a number of right-hand side arguments is greater than 2. So since we're wrapping our function, we want Matlab to behave accordingly. What we can do is basically, there's something called max. There are some special functions that start with max, error, message, txt, something like this. So this is kind of the Matlab printf here, but if you use the Matlab environment and not VS Code, you will see the difference. It will write the message that I'm going to write down here in red as an error. So too many input input arguments. So that's the case because we need exactly 2. Else if number of right hand side is less than 2, for example, not enough, then it's not enough basically. So let's copy this. We can also maybe return from here so that the rest here is not executed to actually not enough input arguments. Yeah, it's kind of a lazy way of doing stuff, but yeah. Now, when we compile this, let's build it. I have to build it twice because of my environment here. And we get an error here. Let's see what the error is. We messed up stuff here. It should be NRHS, number of right hand side, number of left hand side. Yeah. Let's build it. And don't misspell it. There we go, successfully. Now, if we run csum without any arguments, you can see not enough input arguments. If we provide too much, it says too many, but we expect 2. So we can kind of wrap this around and notify the user so that we get basically the exact amount of input arguments as we wish. Now, the way Matlab handles the input arguments and output arguments is as follows. It has the number of left-hand sides, and you can imagine that this is a pointer array. So it means that each argument will be stored here as a MX array pointer. And the same goes for the right-hand side. So what we have to do is we have to extract each pointer, and then we have to get the value that is addressed by the pointer or pointed by the pointer. And then we can just basically retrieve the inputs, for example, 1 and 2 as the arguments. So there's a pointer here. It would look like this. So this is basically an array of 2, the right-hand side actually, and NRHS is exactly equal to 2. So these are basically the definitions if you think about the input that is given here. What we have to do is we have to basically get the pointer, let's say void pointer in this case, PRHS0, and also 1, because we have 2 of them. And this is basically the pointer of 1, and this is pointer of 2 for the example given here. So this one is pointing to 1, and the other one is pointing to 2. So we need to extract the pointers and then dereference the pointers in order to get the values 1 and 2. So this way you have an array of pointers and the number of or the length of that array, so you can handle different situations like we do in Matlab. So you can use basically as many input arguments as you wish. This is basically the abstraction here that is implemented in Matlab for C functions. So we can basically get the m and n values, so the size of our inputs, and we can do this by mx get m, which is basically the number of rows here, and we pass in PRHS 0. So this is basically checking out the size of 1, which is scalar. If this is equal to 1, and I'm going to repeat this for the next argument here. There we go. If the n value, so if it's a scalar, this means actually if this is a scalar. Let's say if. And we are going to do this for the next one too. So and So let's see. The next pointer here, PRHS1, PRHS1, there we go. So get the first argument pointer, get the size m, number of rows, get the number of columns of the first pointer, and then again do this for PRHS1, which is the second argument here. Of course, this should be, oh no, that was actually true. Okay, there we go. Now, if this is the case, then we are good. Else, let's basically copy and paste this stuff and say not implemented yet, something like that. So it should be scalars. If we provide vectors, then we're not okay with that because we have no function for that. So now I want to retrieve double A and B, but I also need a double pointer because everything is a pointer here. Everything is stored in a pointer here. So if we want to retrieve argument 1, what we have to do is we have to get the pointer and use mx get pr, get pointer basically. So we have mx get m, we have mx get n, and we have mx get pointer pr. So we can get the row and column and the pointer itself. So let's get the pointer of PRHS 0, so argument 1. And A should store the value of the dereferenced pointer. So we dereferencing the pointer, and there we go. And we are going to repeat this for the next one here, PRHS1. So there we go. Now we have everything available here. At this point, what we're going to do is we're going to invoke our function. Let's call our function. So you can see that it is kind of a complex function, the max function here, but we have to make sure that all the inputs are as many as we want them to be in the sizes we want them to be. So we have kind of all these saving mechanics here so that we are basically preventing errors and misusage here. Once we're done, then we can basically just have our, for example, result here equals, since I have included and since this is C, I can just combine these. So most of the code is Matlab related here up to this point. So we get basically, we check if we have enough inputs, we check if the sizes are accordingly, and then we get the pointers, we dereference them, get the values. Here we have the values from Matlab. Now we're going to do some stuff here, and then we're going to return this to Matlab and exit, because this function lives throughout this call. It retrieves the input, passes them to C, and then does whatever it should do, and then returns the result of C back to Matlab. So this is kind of a component that we are adding to Matlab, but it is working with C. Now, PLHS, left-hand side. We are just going to return just one thing here, but since this is a pointer vector here, as you can see, we have to allocate memory here. So therefore, we have a function which is called mx create numeric matrix. Numeric matrix. There we go. And since we have a scalar, row and column sizes are 1 and 1. Its data type is mx double class. Do we have anything else? I guess we also provide something like mx real here. So not complex, it's a double, but a real double. As you might remember, we can have something like this, which is a complex double, and then this, which is basically a real double. This mx real stands for this real here. Otherwise, it is a struct as far as I know. So we have allocated memory. So this is allocation. And then we need to get the pointer to this. So let's have pointer mx get pr. Again, we are getting the pointer. So in line 34 or 30, we've done this. Get the pointer of PLHS0, so of this one here. And then the pointer should point to the result. So there we go. This is basically it. And yeah, I guess we're almost done. Let's see. First, we need to compile without any errors, hopefully. And there we go. Yeah, what is the issue now? Let's see. Uh, It couldn't link some stuff for some reason. Why do we have this issue here? MX create numeric matrix. Let's build it again. Seems like I have misspelled it. But okay, now we have the csum function here again. And if I provide one, oh, it's not a capital C, of course. There we go. So we're basically using C now to add these numbers together. Of course, this doesn't seem pretty much exciting, but if it does actually do some interesting stuff, then you can basically implement it like this or embed it like this, and it is quite useful. Let's see, what do we have now? Use max and write a wrapper to compile a corresponding max library, which we did already. Repeat A and B for 2 row vector inputs. Okay, now let's extend this to a vector. Let's see. Let's go in here. Now we have a scalar version here. What about having a vector version here? Instead of having, of course, double A and double B, we're going to have some pointers here. And instead of returning directly the sum, what we have to do is we have to basically create a results vector that's going to be the same size. So let's use malloc. And I guess at this point we need stdlib. So include stdlib.h. There we go. And we're going to allocate len times size of double, whereas len should be provided here. So it's going to be int len. We can use size_t or stuff like that to have positive values here or unsigned int, but I'm just going to skip that for now. This could cause problems if you're working with really long vectors. Then you might exceed the positive upper bound of the integer data type. Then you have to actually use maybe long int, something like that to cover longer vectors, but that's not going to be a problem in this example, so I'm skipping it therefore. So we have actually allocated some memory. We are going to have a for loop, and we have int I equals 0, I less than len, and then I plus plus. And basically result I should be a, I plus b, I. There we go. Of course, we're going to return the result. Now, keep in mind that we need to deallocate or free the memory here, which we didn't do at this point. And this is going to be a pointer at this stage. So I'm going to copy this into my header file. I have another version here, which uses basically double pointer, integer here. So there we go. Now, yep, let's see. This was basically the not implemented part, because if they are not scalars, then they should be vectors. So let's go and try to implement that stuff here. So let's bring this there, and let's actually take this if here. Now we need to check if the sizes are compatible. Now that's going to be an issue, else sizes may not match, so we should maybe create a message where we are not, since we are not able to sum them together. So what needs to happen? Let's see. mx get m prhs0 should be equal to basically to prhs1. So the row should be equal to each other, the number of rows. Is that correct? I guess so. And the sizes, the column sizes should also be equal to each other. Now this could be a matrix, this could be a column vector, this could be a row vector. So therefore, let's get this part, for example, and say that it should be equal to 1. So that row size is now 1. So this is the size of rows, and it should be 1. So there are columns. It means that it is going to be a row vector, if that makes sense. So sizes should be equal to each other in both dimensions, and the first dimension should be equal to 1 in order to be able to use that. So basically, if we look at size, mn equals the size of 1, 2, 3. You can see m should be equal to 1. That's the reason why we say mx get m should be equal to 1. And since they are equal to each other and the column sizes are equal to each other, we should be able to add them to each other. Because we're not able to add two vectors that don't share the size, a matrix dimension mismatch would happen, so we're getting rid of that possibility here. So let's have again our double pointer PTR, and then now we get the length here, which we need. mx get n. So I'm just basically using one of these here. That should give me the length here. There we go. We need a double pointer A. Now these are pointers. Double pointer B. So for the arguments, let's get the pointer. mx get pr of prhs0 and a should be equal to ptr. Since both are pointers, I'm not doing something like dereferencing the pointer and setting that, because it is a pointer. And this one is also a pointer because we have a vector now. And I'm going to just use prhs1, and this will be b. Once we're done with that, now we're going to call our function. There we go. And let's have another pointer, double pointer result, because it's a vector. And C sumvec, that was our function. We needed the A pointer, B pointer, and len. There we go. Now we are going to use PLHS0. That was the same here. You can see up here. Call our function, and then create a numeric matrix here. So we're basically going to do the same here, the allocation part. Let's do that here. Now, of course, our size is 1 comma len, 1 row, len columns, and it is going to be a class, double class real. And we need again the pointer. So let's take that here. Now we need a small for loop, and I'm going to copy that from here because I'm going to copy the whole result here into the memory. So let's paste it here. There we go. Now we're going to copy into PTR the result. So here's a copy, but yeah, we could maybe do it without copying. We can create the numeric matrix here, get the pointer, pass that pointer's pointer to our function here. Then we would have something like double pointer like double pointer result, and it would be void then. It would look like this. This can be done, so we're basically not copying stuff. If the array is big, then we can maybe get rid of the copying here. That's the power of C. But at the moment, we don't really care about that. Now I'm going to free basically the memory that I have created from csumvec here, result. And yeah, that should be actually it again. So let's clear this, let's build this. Hope that we didn't mess up stuff. Let's see. There we go. Now csum can handle numbers, or it says not enough input arguments, which is not correct, but well, you can see it can also handle vectors, and this summation is done by C. So quite interesting to do stuff like this. I basically wanted to show two versions here with a vector example. You can have matrices. Maybe you have, well, some applications, even though that's not maybe control related, you might have some computer vision algorithm in C, for example, like OpenCV. You can embed that. I don't know if it's necessary that much because OpenCV is probably available in Matlab, but you get the idea. If you have some library in C and you want to embed it, you can work your way out and implement your stuff here and embed it to Matlab. It becomes then compatible with Matlab, which is quite powerful because we have so many tools in Matlab, we can combine them easily. It's not wise to try to reinvent the wheel. So it's not actually wise to try to port everything that is in Matlab into C. I would rather add the C part, which is quite important in this case, to Matlab so that we can combine them. Now, let's see. Yeah, we have completed basically the first part here. Now we also have another part, which is about the Simlink S function builder, where we create a custom block for the scalar sum function here. So this first part was about compiling max and adding max capabilities to Matlab. So let's dive into it. Let's clear, and there we go. We're basically done. Let's invoke Simlink. There we go. We have opened up Simlink. Now let's create a blank model. Maybe we should create another folder here. and move stuff. Let's call clear max. You can see it takes some time to clear max. Maybe it's about Simlink, I don't know. But yeah. So let's move all this stuff into part 1 because we don't want to mess up. Move them. There we go. So if I close this, there we go. Now, it takes some time to initialize that. Oh. Let's actually save this under model.slx. Hit the library browser here. And we are going to try to find the S function builder. Basically, we are extending Simlink now. In the first part, we've extended Matlab with some C library that we've developed, so we can use basically the coding interface. But it is also nice to add this stuff into Simlink. So under user-defined functions, we have basically, there are also some examples here. We are going to choose the S function builder, which is basically this one here. So there we go. Now we can maybe close this and zoom in a little bit. There we go. Let's save it. Now, if we double click this S function builder here, we get to here where you can see some interface where we have some functions. And yeah, so basically here we can provide some C code or use some C code because you can see the language is C here. So we can add some libraries, we have some input, output here, we give it a name, and we basically use it. So let's actually use, for example, csum here. Let's see what it is going to do. Let's save it. Now you can see that we have everything did update now. Now you can see we have actually a start wrapper and we have a terminate wrapper. What we can do is we can enter here this custom code part here. So we cannot touch these parts. As you can see, they're blocked. What we can do is we can just write in some code here. Let's printf, for example, the block is initialized. Initialized. There we go. Let's have also semicolon and a new line. And that's it. Now let's also write down a similar message into the terminate wrapper here, which is going to be this part here. Copy, paste, interesting. Let's write it down. Printf, and then the block has terminated. New line. And there we go. Yeah, if we are using plain C, what we can do here is we have real and imaginary parts. We can do this stuff to assign it basically. We are not going to deal with complex numbers here, so I'm going to get rid of this part. But I can basically call this y0 here, which is the output of this block. For some reason, copy and paste doesn't work here. Let's write down y0, 0 is equal to. Now, we can actually add an input here. If we right click and call add input, now we have another input here. So we can have u0, 0 plus u1, 0. Now you can see we are using 0 because it could be an array or it could be a vector. If there are multiple signals coming in, then you can use 0, 1, these indices here to indicate that. And well, basically we have now took the sum here and we're basically returning the value here. So when we hit build, you can see there's a window here and we have some issues. Printf. It seems like we have to include some stuff here. So maybe include stdio.h and there we go. Let's build it again. Let's say okay. Okay. So we again created a max file, as you can see, and this max file is used by this Simlink block here. Now, this is a bit different than what we've done in the first part, and the difference is because Simlink is a more complex environment. In Matlab, we're just calling the function, therefore we need just one wrapper, the max function wrapper, and that's good. And that's enough. But here we have a whole environment, and the way that Simlink runs is going to be first initialization function, then it has this outputs, which is going to be iterated over and over again. It depends on the step and the stop time here. Then once everything is done, once the cycles are done, then we have the termination block. So therefore it's not easy, and I don't really recommend you to try to do it on your own because it is possible, but I wouldn't bother with that. When you have a S function builder, you can basically include your C files or libraries as it was in the first part into Simlink, but you need to use this graphical user interface, in my opinion, so that it is way easier and well, it makes more sense. We've built it, let's override it, and let's test it actually out. Save. We're closing it. There we go. What we can do is we can take some constants. Let's have a constant 1 connected to here. Have another constant connected to here. Have a display. Maybe close that. Now if we run it, we get basically 2 here. And yeah, let's do something like, let's double click it again. We again have this window here. And let's actually printf the value here a couple of times. So yeah, we cannot copy and paste. Interesting. Maybe that's intentional, I don't know. So we're basically reporting the output here. Let's build it. Let's say okay. It's okay. Let's close it. Let's save it. Now if I hit run, we're basically done. But I'm curious because we should have reported it to the screen, but why am I not seeing it? I'm not sure here. Debug. Do we have this window here? Uh, so let's change this to fixed step. Maybe OD45. Solver details. Doesn't really matter. And insisting on fixed step. OD4. Apply that. Say okay. Interesting. Well, let's run it. I'm missing this warning thing here. I don't know why. I should actually see that. So let's delete this. Let's maybe put in a scope to indicate that this is actually a continuous signal. So we will have lots of outputs here. So it is going to be a continuous signal. So we have 10 seconds and then we have a certain sampling time. It just runs once. Why did it change? Fixed step discrete. I don't know why this is not doing what I want here. So let's have 1e minus 2. Let's apply that. Let's say okay. Let's save this whole thing and run it again. Now we're seeing it in discrete. There's only a 2 here and nothing else. Let's double click here. RX0. So here we have language. We can use C, C++. We can insert ports here. That's also possible to do it by right-clicking it. The only thing that I don't get is actually we were able to do some stuff. We were able to see it on the screen because we couldn't see the printfs here. Did we see it here? Nope. Maybe in Matlab's own environment it could pop up in the command window here. But yeah, I'm missing that stuff here for some reason. We can, by the way, also add some parameters, and we can use this parameter value here. It has no dimension. It is a parameter p0. We can give it a name. Let's say, I don't know, let's call it param. Let's save that. And if we do that, if we just build it and save it, Now we have messed up the stuff here. Let's first save. Now we have the parameter here. Now you can see we can set the parameter here. And we can then again open up the editor. Let's see if it's now going to compile. Now it's successfully compiled. And yeah, now we have the parameter param, and as far as I remember, we can use that inside of our function here. So it should be actually we should be able to use it like param. Let's see if it's compiling here. Maybe param 0, I'm not sure. Let's see. So now it's complaining about param. Oh, maybe we should change it to float because we're in an environment where this is float. Let's try it again. Let's also give it a dimension here, if it's possible. Now we cannot change the dimension of the parameter. Let me just quickly test this out. Yep, it created it. Now let's save it. And let's run it. Now we can see the value here is offsetted. And we can basically define parameters. These would be nice if we have, for example, a certain simulation, and then we have like a mass spring damper system that we've implemented in C somehow. Then these could be like mass spring damper coefficients, and then you can just give the coefficients and your simulation works with that. Because we can access it in the code itself, it's quite powerful if you think about it. And yeah, I'm just going to try something like fprintf. If that's not working, I'm giving up. It should show up in our warning screen here. Maybe I don't remember it correctly. Yeah, it failed because we don't have the file thing going on here. So yeah, let's take it back. Let's build it back. Let's close this. Let's close that. Let's add a display. Let's connect that. Let's run it. Now we can see it is 3 because of the parameter here. If we double click it and change it, the result will also change. So yeah. Now, actually I found out the printf issue here. I looked it up again. There is a max printf version that we should use when we display stuff. It should be max printf, not the usual printf. we can still do that, but of course it doesn't make that much sense. And then we have basically max printf. There we go. And let's build it. Let's say okay. Let's close it. Let's save. So everything is updated now. And if we run it, now we get some diagnostics. And that's exactly what I was trying to do. The block is initialized, we get the values, and then the block is terminated. Now, of course, we're working discrete, so that's not my intention at all. I want to have basically a continuous execution here. Fixed step OD4. We have some solver stuff going on, but yeah, it uses just 2 steps, which is not ideally what we want here. Sample mode, we can change it to continuous. Say okay. Say okay. Compile it. And then save it. Now let's run it. Now you can see it did work continuously. At each cycle, we've printed out what we wanted here. At the initial step, it just initialized the block. Then for each cycle, for each sample time, we get the result here. And then the block has terminated. Now, if you look at this, this is exactly what it looks like. Of course, since it's still plotting in discrete mode, we get this weird behavior here. This is actually a line at 3. So that's that. Now here we can see that actually we can add some external functions like this one here. As you can see, we can have external functions, double func double a, so something like this, for example, and we should add that here. So we can basically add it in here. There we go. We can add path, entry, and stuff like that to be able to compile stuff like external functions or libraries. Sometimes they need external flags. We can provide that here. And that's pretty much it actually about the S function, because we have 3 different states, and here we're continuously calling the summation. Here we have also the parameter. You can have a specific function which you have defined here externally and then call it here as we would do in the max function, the first part that we've done today. Now if we look at the result that was generated here, we have a csum function here. This is the S function. It has lots of definitions here. You can see it has outputs, parameters, and then stuff about that. We have some special structures here and the initialized sizes. So it is quite complicated to use the Simlink to embed stuff into Simlink, but fortunately we don't really have to deal with all the stuff here. It does it on its own. And you can see here, actually, this is the function that we're basically modifying from the graphical user interface. I wrote makes printf, this block is initialized. This code is belonging to me, and this one too. So you can see the interface is just used to do stuff like this. And at the end of the day, you have a csum max file, which is basically also the case in the first part. So yeah, the only difference is here we might add some C functions and then address them from there and add them to the compilation, and that's basically it. So yeah, hope that this was helpful. You can view the PDF. I have all the stuff here down. I have also a quick demo how to use this. You can basically extend Matlab's capabilities with C libraries. You can also embed it into Simlink, In Simlink, we can use the S function builder. You can use C++ and C, so there are two versions to that. But I wanted to stick with C because most of the libraries are in C. And if you're in C, you can also just migrate to C++. No big deal, I'd say. So yeah, this is basically it. We have embedded. There are also direct calls to C function and stuff like that. But if you use the S function builder, you can kind of incorporate a bigger library into it. If you're just going to call just one function, then you can also provide it as a C function. But S functions are quite useful. And this is not the only version. You can check out the other versions of the S function, but this is a low-level C function embedding example here in this case. So hope that this video was helpful.